In this video, we are going to learn how to use linear programming to maximize profit. We'll start with an example. You are screen printing t-shirts and sweatshirts to sell at the Polk County Blues Festival and are working with the following constraints. You have at most 20 hours to make shirts. You want to spend no more than $600 on supplies. You want to have at least 50 items to sell. And now, a one-color t-shirt that takes 10 minutes to make, it costs $4 in supplies, and you can make a profit of $6. For a three-color sweatshirt, it takes 30 minutes to make, the supplies cost $20, and the profit is $20. Now, how many t-shirts and how many sweatshirts should you make to maximize your profit, and how much is the maximum profit? So this is a lot of information to digest. So we're going to break it down a little by little. Starting with labeling our variables. We're going to let X be the number of t-shirts. We're going to let Y be the number of sweatshirts. And we're going to let this last column over here be the total whenever you combine t-shirts and sweatshirts. Let's start with the number of minutes it'll take to make all of these. Now, t-shirts should take 10 minutes to make, and sweatshirts should take 30 minutes to make. So we'll do 10x, so 10 minutes per t-shirt and 30 minutes per sweatshirt. Now, total amount of time that we have is 2 hours. So we can't put 20 here because right now 10 and 30 are in minutes. So we just need to convert 20 hours to minutes. So that's just 20 times 60, which is 1,200 minutes. Now let's look at the number of items we can sell. Now, that's just X and Y because we let X be the number of t-shirts and Y be the number of sweatshirts. But now the total number there should be at least 50. And now let's look at supplies. So let's look at the cost of this. It's going to cost $4 per t-shirt, so 4X, and $20 per sweatshirt, so 20Y. And we don't want to spend more than $600 on supplies. And lastly, let's talk about the profit, since this is what we want to maximize, as it says, maximize your profit. We're making money at $6 per t-shirt, $20 per sweatshirt, and together we don't have a constraint for the maximum amount of profit, but we just want to find out what that is. So our total is just going to be 6x plus 20y. And that makes up our objective function, which I'm going to write over here. P, profit, is equal to 6x plus 20y. That is what we're going to try to optimize, meaning find the maximum of. But now we need to write our constraints down. Now we've really organized all the information, so I can make a constraint on minutes. I can say that 10x plus 30y is the total amount of time we're going to spend, and that time needs to be less than or equal to 1,200. The reason why it's less than is that I can't go past 2 hours. So any more than 1,200 minutes would be more than 20 hours. Next up, the number, x plus y, is the total number of number of items we'll make. And we'll see here that we want to make at least 50. So in this case, I don't want to be less than or equal to 50. I want to be greater than or equal to 50. So I can still make more than 50, but at least that much. And lastly, we have our cost, which would be 4x plus 20y. In this case, we don't want to spend more than $600, so this has to be less than or equal to 600. You'll see here as well with the cost, it's $20 per sweatshirt, and my profit is $20 per sweatshirt. Now, on initial view, you might think, oh, that just cancels each other out. But think of it more as it costs $20 to make, but we sell it for $40, and that's why we make a profit of $20. Now, the last two constraints we want to write down are x is greater than or equal to 0, and y is greater than or equal to 0. These are implicit constraints because I don't want to have a negative number of t-shirts that I'm going to sell. I'll let it be 0, but it can't go less than 0. Now let's get into graphing, because now we need to find our feasible region so we can understand what points we can plug into our objective function. We're going to start with this 10x plus 30y is less than or equal to 1200. So subtracting 10x, we'll have 30y is less than or equal to negative 10x plus 1200. And then dividing by 30, we have y is less than or equal to negative 1/3 x plus 40. So we have a y-intercept of 40. Now, one thing I want to note is the graph I've drawn so far. The y-axis counts by 5s, while the x-axis counts by 10s. So I can't just do a normal rise and run here because it's not equal at both axes. So I have to be very careful. This is actually a big mistake that lots of students can make when graphing. So what I'm going to do here instead is I'm going to start with this y-intercept, and I'm going to find the x-intercept of this graph just to find my 2 points pretty quickly. So if I were to let y be 0 and solve for x, then I would subtract 40 and then multiply by negative 3, which gives me 120. So I can find the y-intercept and the x-intercept rather quickly and then just draw a straight line through the two of them. This is another way to graph. Now, and this does keep going, but I'm only concerned with what's going on in this first quadrant. So I'm going to shade below the line since it's less than or equal to, and I'm in this quadrant. Now next I'm going to graph x plus y is greater than or equal to 50, which is a pretty quick one because we just subtract x and we're done. But we get a y-intercept of 50. And again, to graph this, I'm not going to use the slope of negative 1 because that would really be down 5 over 10, which is negative 1/2. But I'm going to find its x-intercept by making y 0, and I'm going to see here if y was 0, x would be 50. You could also have counted it as down 2 here, and made down 10, and then over 10, which would be negative 1. But I'm showing you an alternate way to graph. I'm taking my time to really get a nice line. And I'm above this line, so it's everything within this triangle now. So now we're in this kind of area. Now let's graph our last line. Again, the last two constraints we don't need to graph. We're just going to keep it in the first quadrant. But our last one here, we have 4x plus 20y is less than or equal to 600. We'll solve for y. We'll subtract 4x. So 20y is less than or equal to negative 4x plus 600. Divide by 20. We get y is less than or equal to negative 1/5 x plus 30. So I'm here, and again, its x-intercept when I make y 0 will be 150. So way out in that corner over there. And we're less than this line. So it'll be everything in this feasible region right here. In this shape. Now we're nearly there. We're going to label all of our vertices of our feasible region because those will be where our maximum minimum could take place. So again, I'm going to make this bottom left point here. I'll make that Q. This one up here, R. This one right here, S. This one, T. So the point Q would be the coordinate 50, 0. R would be the point, It's right in between the two, so 25, 25. S would be the point. It's in between the two again, 75 and 15. And T over here on the right would be 120, 0. And now we're going to plug these into our objective function to see which one gives us our maximum and which one gives us our minimum, with our focus being on what the maximum is. So plug it in Q first. I'll have 60 times 50 plus 20 times 0, which 6 times 50 is 300 plus 0 would give me 300. R, I would get 6 times 25 plus 20 times 25, which again, 6 times 25 is 150. 20 times 25 is going to be 500. So 150 plus 500 be 650. Plug in point S, we'll have 6 times 75 plus 20 times 15. 6 times 75 will be 300. 20 times 15 will be 300 as well. So we'll have 600 there. I'm just going to double check my math. Oh, made a mistake. 6 times 75 should be 450, and 20 times 15 should be 300. So that would be 750. And lastly, we'll plug in T, which would be 6 times 0. Oh, sorry, 6 times 120 plus 20 times 0, which will give me 720. And looking here, I can see my maximum is going to be $750. My minimum is going to be $300, but I'm just looking for that maximum. So I'll make $750 at most. And how many of each should I make? I should make what looks like, this is point S, 75 t-shirts and 15 sweatshirts. And that is how you use linear programming to maximize profits.